Today's Range Rover EFI combines state-of-the-art electronic fuel injection technology with a legendary reputation for the ruggedness and reliability of our V8 engine. At first glance, under the bonnet, the sight of all those pipes, ducts, valves, sensors and electronics may be overwhelming. So to enable you to service EFI, diagnose problems efficiently and make the repair right first time, it's important that you become familiar with the location of all the components and how they work. This video and the accompanying training manual, which covers the subject in greater detail, will help you to do just that. The two items, the video and the manual, must be studied together if you are to gain maximum benefit from the training program. EFI comprises three different systems: a fuel system, an air system, and an electronic system. They combine to produce the correct air-fuel ratio under all conditions. And the mastermind behind it all is the Electronic Control Unit, or ECU, as it's called. To help you understand, we'll look at each system separately, starting with the fuel system. In diagrammatic form, you can see the fuel pump P. It pumps fuel through the supply line S via a filter F to the fuel rail around the engine's plenum chamber PC. The 8 fuel injectors, numbered 1 to 8, are supplied direct from the fuel rail. Excess fuel returns to the fuel tank via the return line E and a fuel pressure regulator R located in this return line. Now we'll look at the individual fuel components in more detail. The fuel pump is located in the fuel tank. It is submerged in the fuel and is electrically operated. Diagrammatically, the pump looks like this. It contains an electrically operated permanent magnet motor which drives two pumping elements: a low-pressure vane-type pump LP and a high-pressure roller-type pump HP. There are two valves, a non-return valve NR and an excess pressure relief valve PR. When the pump is energized, the low-pressure vane pump LP draws fuel in through a filter to prime the system. The high-pressure roller pump HP boosts the pressure and forces the fuel to the injector supply line via the non-return valve NR. Any excess pressure developed by the pump simply lifts the pressure relief valve PR off its seat and allows fuel to return to the tank. Next in the supply line is a fine mesh filter mounted on the chassis. This filter has to be changed at specified service intervals and must be fitted the correct way round. An arrow on the filter body shows the direction of fuel flow. From the filter, fuel passes directly to the fuel rail and to the 8 injectors. The 8 injectors are fitted into the inlet manifold and inject fuel into the airstream near each combustion chamber. Each injector contains an electrical solenoid which, when energized, lifts a needle valve to allow injection of the pressurized fuel. When the solenoid is de-energized, the spring snaps the needle valve closed. The length of time the injectors are open, and therefore the amount of fuel that is injected, is controlled by the ECU. The injectors are linked to open in banks of 4, 1, 3, 5, 7, or 2, 4, 6, 8. Signals from the distributor via the coil will tell the ECU to open one bank of injectors or the other. As we will see later, the ECU analyzes information from other sources to determine the period of time each bank of injectors shall open, and therefore how much fuel is injected. This open time is critical to engine performance. If it is incorrect, then economy, exhaust emissions, engine performance will suffer and give unnecessary rise to the customer's blood pressure. The final component in the fuel system is the pressure regulator, which is fitted in the end of the fuel rail after number 8 injector. Its purpose is to vary the fuel pressure in inverse proportion to manifold depression. Let's see if we can make this clearer. If the regulator were not fitted, a high manifold depression D would generate a high suction and therefore draw more fuel from the injectors J during a given injector open time. Conversely, a low depression would create less suction, and so less fuel will be drawn. So the pressure regulator is fitted to give a lower fuel pressure when depression is high, for example, at idle, and a higher fuel pressure when depression is low during acceleration. The regulator contains 2 chambers separated by a diaphragm R1. One chamber contains a spring R2. The regulator works like this. Fuel pump pressure F is applied to one side of the diaphragm, whilst the side containing the spring is connected to the manifold. When manifold depression is low, the pump has to force the diaphragm against the spring to enable excess fuel pressure to return to the fuel tank via pipe E. Therefore, fuel pressure remains high. When the throttle is closed, manifold depression increases and pulls the diaphragm against the spring. This allows a greater volume of fuel to escape through pipe E back to the fuel tank and causes a drop in fuel pressure. In this way, pressure is varied inversely with manifold depression, and therefore the amount of fuel injected is solely dependent on injector open time. This completes the component parts of the fuel system. Next, we will examine the air system. Air entering the engine passes first through a filter and then through the airflow meter A. The throttle butterfly T, linked to the driver's accelerator pedal, controls the volume of air entering the plenum chamber PC, which distributes the air down 8 ram pipes to the combustion chambers. The first component of the air system we will examine is the airflow meter. It's located between the air filter on the right and the throttle butterfly housing on the plenum chamber on the left. Incidentally, there are 2 air adjustment screws, a mixture adjustment screw on the airflow meter and an idle speed adjustment screw on the throttle butterfly housing. In section, the airflow meter looks like this. The air passage contains a double flap, mounted on a flap spindle FS. One flap is the measuring flap MF, and the other is the compensating flap CF. The measuring flap is closed onto its stop by a light spring FR, and is opened by air being drawn into the engine. When this happens, the amount of movement of the flap, and therefore the volume of air entering, is measured by the airflow meter potentiometer AP. Flap movement is converted by the potentiometer into electrical signals to the ECU. One further item to be seen in the illustration is the fuel pump switch contacts FPC. When the flap is at rest, that is, when the engine is not cranking or running, the switch contacts are held open and no current can pass to the fuel pump. When the engine is cranked, air being drawn in past the throttle butterfly TB will pull the measuring flap off its stop and turn the flap spindle. This movement will allow the fuel pump contact points to close. The pump will now operate and the engine can start. When running at idle, air will be drawn through the air bypass port CO with its mixture adjustment screw, and also around the throttle butterfly bypass port IS with its idle adjustment screw. As the driver accelerates, throttle movement will be read by the throttle potentiometer. The extra air required will pull the airflow meter measuring flap further open, and this movement will be noted by its potentiometer. The compensating flap moves into chamber D, where the fit of the flap in the chamber ensures that its movement is damped. You will find a more detailed explanation of the airflow meter in your training manual. Now let's look at some of the pipe connections and components mounted in and around the plenum chamber and see how they operate. First, the extra air valve. It's mounted on the inlet manifold coolant gallery and is sensitive to coolant temperature. It contains a disc valve, DV, mounted on a spindle, and a bimetal B, which has one end in contact with the disc valve. The other end of the bimetal has a heating wire H coiled around it. In this illustration, the system is cold. The bimetal is holding the disc valve in such a position that depression from the plenum chamber will draw air through the valve as indicated. As soon as the engine cranks and runs, current will pass through the heating wire and start to warm the bimetal. As it warms, the bimetal will bend and allow the coil spring to pull the disc valve closed progressively, thus shutting off the extra air supply. Obviously, to maintain the correct mixture during cold starts, more fuel is needed. It is supplied by this cold start injector, which sprays directly into the plenum chamber. It is controlled by this electrical thermotime switch mounted in the inlet manifold coolant gallery. Incidentally, don't confuse the thermotime switch with this coolant temperature sensor. Another connection to the manifold is this pipe, which provides vacuum to open the flap in the vehicle ventilation system. It works like this. When the driver moves the controls to fresh air and fan on, the solenoid valve SV is energized, and the vacuum servo unit VU opens the flap. The vacuum reservoir VR ensures that the flap operation is not affected by significant changes in manifold depression. Next, crankcase ventilation. This pipe connection near the throttle butterfly provides the necessary depression to draw a measured volume of air through the engine crankcase via the filter F and the oil separator OS before being burned in the combustion chambers. Incidentally, for some markets we have to fit a fuel evaporative loss system using this charcoal canister. It works on the same principle as the crankcase ventilation system, using vacuum to prevent toxic fumes escaping to atmosphere. Two other plenum chamber connections to mention are this brake servo connection and this solenoid-operated air valve. It is only fitted to vehicles with air conditioning to increase idle speed when the compressor cuts in. For convenience, it takes its air supply from the pipe to the extra air valve. When the compressor cuts in, the valve opens to allow additional air into the plenum chamber. So you can see there are numerous potential air leak points. All hoses and connections must be airtight for EFI to work correctly and efficiently. Later, we will discuss procedures to check for air leaks. One other point to mention. These two pipes supply coolant to the inlet manifold hotspot MH under the throttle butterfly to assist warm-up. Let's take a break now. Discuss among yourselves what you have seen, and for more detail, read the fuel and air system operation chapters of your training manual. Stop your player now and restart it when you are ready to continue. Now we'll move on to the electrical system. Yes, this diagram may look a bit frightening, particularly if you are not an electrician. So let's break the system down to its component parts to make it easier to understand. We'll start with the electronic control unit, or ECU as we call it. It is located under the right-hand front seat and is the brains of the operation. The ECU decides how long the injectors stay open and therefore how much fuel is injected. To do this, it needs information from a number of sources. It needs to know the position of the ignition key, whether it is off, cranking or running. It must also know the position of the throttle so the driver's accelerator pedal position can be interpreted. Other things it needs to know are engine speed, by measuring the ignition pulses from the coil, coolant temperature, the temperature and volume of the air entering the engine, and it must also know the state of charge of the battery. Now we'll look at where these sensors are and how they work. First, the airflow meter. It has a multi-plug connector on top of the housing, which contains connections to 3 separate electrical components in the airflow meter. One of these components is this air temperature sensor, mounted in the airstream to measure air temperature as it enters the engine. Diagrammatically, the air temperature sensor is shown here as ATS. Other electrical components in the airflow meter are the AFP, airflow potentiometer, and FPC, fuel pump contacts. The airflow potentiometer is attached to the flap spindle to measure the volume of air entering. The fuel pump contacts close when the flap moves to allow current to the fuel pump. If these contacts are faulty, the pump will not operate. Now, the throttle potentiometer. It is mounted directly onto the throttle butterfly spindle so that it can note movement of the driver's accelerator pedal. This is how it is shown electrically in your training manual. The potentiometer wiper is connected to the butterfly spindle, and when the throttle position alters, information is sent along the red wire R to pin 2 of the ECU. These 3 components are located under the front right-hand seat. The main relay MR is at the bottom. The steering module SM is the red unit in the center, and the fuel pump relay FPR is at the top. Electrically, you can see both relays contain contact points, operated electromagnetically. Current to the relays to close the points is supplied through the steering module SM. In the main relay MR, current direct from the battery enters at terminal 3051. When the points close, this current will be supplied to the airflow meter to pin 10 of the ECU and to the power resistors for the injectors. The fuel pump relay, FPR, receives current at terminal 3051 from the ignition switch. When these points close, current passes to the fuel pump and to the extra air valve. Next, the overrun fuel shut-off relay on the left and the vacuum switch on the right. The relay is mounted on the bracket which supports the airflow meter. The vacuum switch is located near the fuel pressure regulator and shares a common vacuum connection to the plenum chamber. The overrun fuel shut-off relay, OFSR, contains a pair of contact points which are a direct link from the distributor and coil to pin 1 of the ECU. The points are closed by an electromagnet through which current can pass whenever the vacuum switch VS is closed and the ignition is on. In fact, the only time the vacuum switch opens is under conditions of very high manifold depression, such as decelerating from high speed with a closed throttle. In these situations, the vacuum switch opens, causing the overrun fuel shut-off relay points to separate so the injectors cannot operate. The last electrical items we will discuss are the injectors and the power resistor pack. The power resistor pack is mounted on the airflow meter bracket and is required to reduce voltage to the injectors to approximately 3 volts. Whenever the engine is cranking or running, current reaches all the injectors from the ignition switch IS via the main relay MR and the power resistor pack PR. However, the injectors will not open until instructed to do so by the ECU. You can see that the connections from the injectors to the ECU are linked within the ECU in 2 banks of 4, 1, 3, 5, 7, and 2, 4, 6, 8. Whenever the engine is cranking or running, the distributor and coil send a pulse as each plug fires via the overrun fuel shut-off relay to pin 1 of the ECU. As we said before, these pulses are used by the ECU to energize either one bank of injectors or the other. The amount of time the injectors are energized, that is, held open, is decided by the ECU from information received from the sensors. There is not time to discuss all the sensors in this program. However, you will find them in greater detail in the training manual. In addition, the manual contains 4 diagrams which show the electrical circuits in operation in each of the following conditions: ignition off, ignition on, engine cranking, and engine running. Before we start to look at problem solving, read the electrical system operation section in your training manual. Stop your player now and restart it when you are ready to continue. In the final part of this program, we will discuss fault diagnosis. EFI is a sophisticated installation, and at first sight, fault diagnosis may appear difficult. But with the knowledge of how EFI works, the aid of a digital multimeter, such as one of those shown here, and an ability to follow a systematic procedure, you have got a head start in problem solving. First, let us say that EFI is very reliable. Most problems are not caused by the EFI system itself and are much more likely to be elsewhere. For example, a slack accelerator cable or carpet under the pedal so that full throttle can't be achieved. A clogged air or fuel filter. Incorrect ignition timing. Plug leads fitted incorrectly, poor compressions, and so on. However, If you are convinced that your problem lies within the EFI system, then start by examining the throttle linkage. Adjustment of the butterfly linkage and the throttle lever are given in the training manual. Then check the throttle potentiometer adjustment like this. Switch on the ignition. Connect a voltmeter between the red and green leads at the potentiometer multiplug. The voltmeter should read 325 millivolts plus or minus 35 millivolts. If the reading is wrong, slacken the two screws and turn the potentiometer one way or the other until the reading is correct. Then tighten the screws. Operate the throttle a few times to settle the adjustment and recheck the voltmeter reading. Next, check the ignition timing. The idle speed. The adjustment screw is next to the throttle butterfly. And the idle CO level. The CO adjuster is the screw fitted in the airflow meter. If you still have a problem, and you are sure it's an EFI problem, then the next step is to examine the plugs. Take them all out and keep them in strict cylinder order. Left bank 1, 3, 5 and 7, and right bank 2, 4, 6 and 8. Examine the colour. If they are all grey, then there is no obvious problem with the EFI air or fuel systems. Of course, if only one plug is an incorrect colour, this will tell you that there is a fault specific to that cylinder. It may be a faulty injector, but it may also be a fault in the plug or its lead, a faulty valve, and so on. However, if the plugs are all white or all black, or if one bank is a different colour to the other bank, as you see here, these are all clues as to a possible EFI fault. You will find a diagnosis list in your training manual. If you think the problem is air-related, start by thoroughly inspecting the trunking between the airflow meter and the throttle butterfly housing. Make sure there are no holes or splits in the laminations, and that both retaining clips are tight. If the trunking is okay, you must now start thinking in terms of a leak at one of the many connections to the throttle butterfly housing and plenum chamber. To pinpoint a possible air leak, carry out the following procedure. At the rear of the engine, disconnect at the plenum chamber the vacuum pipe to the regulator and to the vacuum switch. Connect a vacuum tester to the pipe and evacuate the system. Check that the vacuum doesn't drop. If it does, it means that there is an air leak either in the piping, or in the regulator, or the vacuum switch, which must be rectified. If the vacuum holds, those components are airtight and must be reconnected so that the regulator can function when the engine is started. Disconnect the brake servo pipe. Then seal the connection at the plenum chamber. Then disconnect the ventilation fresh air flap vacuum pipe and seal the connection. Disconnect the extra air valve pipe at the plenum chamber and seal the plenum chamber. Disconnect the other end of the extra air valve piping, where it attaches to the throttle butterfly housing, and seal the housing connection. And if a charcoal canister is fitted, its vacuum pipe connection must also be sealed. Disconnect the crankcase ventilation pipe from the throttle butterfly housing and seal the housing connection. If air conditioning is fitted, disconnect the air valve pipe at the plenum chamber and seal the plenum chamber connection. You have now checked the pressure regulator connection and sealed off all the other air and vacuum connections to the inlet manifold. So start the engine and see if there is any change to the idle. If there is no change, you have proved that all the items disconnected are airtight. In other words, the components and their connecting pipes are not leaking air. If the idle speed has altered, one of the disconnected components or its pipework is faulty and must be pinpointed. So start by unsealing and reconnecting one component, say the brake servo pipe. Then recheck the idle. If it has changed again, this means that the fault lies either in the pipe to the servo or in the servo itself. You have now isolated the problem area and can investigate that area to pinpoint the fault. If the servo is okay, carry on reconnecting the other components systematically, checking the idle after each reconnection. If each component checks out correctly and the problem still exists, then you must start looking for an air leak elsewhere. This could be a leak past the two plenum chamber seals, past the injector seals, including the cold start injector gasket, or past the manifold gasket. To test, start the engine and squirt a small amount of oil systematically around each suspect area. An air leak point can usually be either seen or heard as the oil gets sucked in at that point. An excessive amount being drawn in will create blue exhaust smoke. Once you have found and fixed the air leak, don't forget you will then have to readjust the idle speed and the CO level. Both, of course, will have altered. Now a word about causes of black plugs. This may be due to excessive fuel or insufficient air if, for example, the air filter becomes blocked. If the problem is overfueling, this may be due, for example, to incorrect information being supplied to the ECU, which causes the injectors to stay open for too long. It may be a faulty coolant temperature sensor, signaling engine cold when in fact it is hot. Or it may be high fuel pressure caused by a faulty regulator. You will find further test details about this in your training manual. Before we finish this program, a word about the electrical tests listed in the manual. As we said before, EFI electrics are very reliable and cause few problems. But if you have made all the other tests and the fault still exists, then carry out the electrical tests in the sequence shown in the manual. Some tests check voltage and the others measure resistance. A test instrument like this digital multimeter is the only accurate means of checking the specified resistances and voltages. Make sure you follow each test exactly as laid down. Let's look at test 1. It's to check the permanent voltage supply to the main relay. The ECU multiplug is connected for this test and the ignition is off. Connect the voltmeter between terminal 3051 of the main relay and earth. The voltmeter should read 11 to 12.5 volts. If it is below 11 volts, check the battery state of charge, the earth connections, and the brown wire connection to the main relay. If everything is okay, move on to test 2, and so on through to test 16, or until you have pinpointed the problem. That completes this training program on the Range Rover EFI system. Review it if it will help your understanding. And as we said before, make sure you study your training manual. Help us to help you to give your customers trouble-free motoring. It will pay you in the long run.